All right. Good afternoon, everyone. Thank you for joining me and the team from Continuum, Oregon State University, and Rev-Tec for this fascinating presentation on a new approach for high-performance materials for additive manufacturing. I'm Scott Dunham. I'm going to be your host today. I'm representing additive manufacturing research. We'll do some introductions on everybody here in just a second. I just want to talk just very briefly about the powder supply chain for additive manufacturing, just to kind of set the stage for this presentation. This is a topic that's very important to us here at Additive Manufacturing Research. Definitely something that's been in a state of evolution for the last decade. This year is certainly no exception. AM Research, we track the additive powder market and its growth on a quarterly as well as an annual basis. Last year, we saw a lot of interesting things. The hardware market, for additive manufacturing, as many of you may know, has been struggling with high interest rates and various other challenges, but the powder market has maintained a steady growth trajectory. As the existing and established power users of AM keep finding ways to leverage the technology and therefore use powders, we expect this market to eventually, in 2025, cross the $1 billion in valuation mark for the first time in its history. And we continue towards reaching a milestone maybe in 2026 by our forecasts of around 10,000 tons of powder consumed by the AM industry. Growth isn't a guarantee, though, and eventually, if printers keep being challenging to adopt and prove their value, then the downstream effect is obviously going to hit the powder market. That's why I'm excited to introduce this discussion today, because it centers around continued innovations in the powder supply chain that are going to help invigorate adoption of additive technologies as a whole. So let's start off with some introductions. Today, we're going to hear from a number of speakers. First, from Oregon State University, we have Drs. Carl Hoppala and Kamyar Raufi, who are going to take us through some of the challenges and talk about the importance of nickel specifically as a material in a changing manufacturing landscape. And then later, we'll hear from the team at Continuum, represented by Sunil Badwe. Dr. Sunil Badwe, and then we're actually going to pass it to the end user perspective with Mike Forelli, who is president of Rev-Tec as an end user of additive manufacturing and using some of these materials. So with that, I'm pleased to pass it over to Carl and Kamyar from Oregon State University.
Yeah, thanks, Scott. So I'm Carl Hoppala. I'm a professor here in the School of Mechanical, Industrial, and Manufacturing Engineering at Oregon State University. It was a pleasure working with Sunil and others with Continuum on this study. I'll turn it over to Kamyar Raufi, who is going to give you a little bit more information about the motivation for doing this study, as well as the results of the study and kind of the methods that we undertook with the study. So Kamyar, take it away.
Perfect. Thank you. Hello, everyone. So actually, I'm going to talk about some of the motivations and the background that we had for this study, starting with the strategic importance of nickel in a changing manufacturing landscape. So we know that based on some rising concerns about global warming, climate change, resource scarcity, sustainability, and public awareness, industrial sector is under increasing pressure to reduce its environmental impacts, including those of supporting materials and manufacturing processes. One of the main critical minerals in the U.S. Is nickel, based on its strategic, economic, and security value, and it actually plays an essential role in alloying within the steel industry. We know that additive manufacturing also is a transformative, driven by expanding applications across industry sectors like food and consumer products, healthcare, automotive, aerospace, and construction. Now, based on the superior mechanical properties, excellent resistance to corrosion and oxidation at high temperature, and high wear resistance. We know that production of nickel-based superalloys using AM or additive manufacturing has gained strong interest in high-performance sectors. That being said, use of recycled nickel-based alloys in powder manufacturing saves energy, increases service life, and reduces maintenance demands compared to virgin materials. Now, considering all of these factors and elements together, considering the sustainability concerns and topics, and also based on the advent of using AM manufacturing processes for making different products and products in different sectors, as well as use of nickel. The objective of this research was to assess the environmental impacts of producing nickel powder using life cycle assessment. And I'm going to briefly talk about life cycle assessment, or LCA, in the future slides. And to conduct this study, actually, we considered 3 production scenarios. So the first scenario considers 100% virgin nickel. The second scenario and the third scenario both use actually recycled nickel, but in scenario number 2, we have various suppliers to manufacturing facility, which is located in Cloverdale, and we have no carbon offset for to consumables and to utilities and transportation. But for the third scenario, the manufacturing facility is located in Houston, and there are local suppliers who provide the raw material for making the powder in the facility, and there are carbon offsets to utilities and transportation. So let's take a look to the life cycle assessment framework and the methodology that we applied here, which starts with goal and scope definition. So under the goal here, as I explained in the previous slide, the main objective was to investigate the impacts and to assess the environmental impacts of making nickel powder based on different technologies and different scenarios. And the scope here focuses on cradle to gate life cycle, which starts with raw material extraction, transportation activities, and processing that raw material and making that ready for final manufacturing and manufacturing step. But in addition to cradle to gate life cycle scope, if we want to expand it, there are 2 other phases and steps, which are use phase and end of life, which are not included herein, and expands the cradle to gate life cycle scope to cradle to grave. But here we only focus on the first 3 steps, which were transportation, raw material extraction, and manufacturing. And also here we have the functional unit definition, which is about making 100 kilogram of nickel powder based on each of those 3 scenarios. Step number 2 actually captures the data, which is life cycle inventory analysis. For making all of those processes and actually for making all of those products and to reflect them on the software that we applied here, we need to capture some data for each of those steps and for each of those inputs. So the data, again, I will explain and I will show you part of the data in the next slides, but it was captured based on the feedback from industry experts as well as literature, academic literature and some papers. So we were able to capture the data needed for conducting the life cycle assessment. The third step actually conducts that life cycle assessment based on the data that was captured in the previous steps. And finally, we have interpretation to capture the hotspots and the areas that have been found as the main contributors to the environmental impacts and how we can make some improvements and to have a better sustainability performance. So here we have like an overview of the 3 scenarios for making the nickel powder. So you can see that on the left side, everything starts with like ore extraction and raw material processing, because first scenario, as you can see on the bottom, is 100% virgin nickel. So after extracting the raw material, it needs to be transported to the facility, which is located at Cloverdale for the first scenario, and it uses conventional nickel gas atomization. The second and the third scenario, as I mentioned earlier, and as you can see here on the right side, they mainly use recycled nickel for their manufacturing and for making the powder. So based on the location of the suppliers, we have some sort of transportation activities, and the main manufacturing process here is nickel plasma arc atomization, which includes feedstock preparation and the atomization process itself. And then you can see that the powder and the scrap coming from this process is also used again as some sort of raw materials or inputs, again as another cycle for the next cycles of plasma arc atomization in the process. Once the powder is provided and created, the next following steps are sieving, loading, and packaging. But you can see that here again, in terms of the system boundary that was captured for this study, those three steps, I mean sieving, loading, and packaging, are not included due to their minor impacts on the sustainability performance and in the assessment. So the main contributors for powder production are within these transportation activities, or recycling the raw material, or extracting raw material, and the manufacturing process itself. Here is like some inputs, material inputs for each of the scenarios. So for scenario number one, the atomization process yield is 25%. This is a number that also be included and we considered for the other two scenarios as well. And you can see that there isn't any internally recycled or externally recycled raw material for this scenario. And all the 400 kilogram virgin material is provided from the mine, and the manufacturing facility is located at Cloverdale. For scenario number two, again, the atomization process yield is 25%, but here we have 200 kilogram internally recycled raw material powder, and actually 120 kilograms coming from externally recycled powder. And for the suppliers, you can see that in the table below that we have three suppliers providing that raw material, I mean, recycled material for making the powder in Cloverdale. And the third scenario, similar to scenario number two, actually have 200 kilogram as internally recycled material and 120 kilogram as externally. But the manufacturing facility is located in Houston, and also it uses some local suppliers to provide that recycled material for making the final product. Here we have some sort of the material and energy inputs for nickel powder production, which actually captures step number two in our life cycle framework. So you can see that most of the data was captured from the industry experts, and also we had some papers and some articles in the literature for capturing some of the other data for conducting the life cycle assessment. Now, for the third step of the life cycle assessment, which includes in conducting the life cycle assessment, we have like three methods. On the very left, you can see CED, which stands for cumulative energy demand. The second one is global warming potential, and the last three, human health, ecosystems, and resource availability, are the three endpoint impacts on the recipe method. As you can see, like all the trends for these three methods are the same. So for the next slides, and actually for the next assessment, we only focus on global warming potential to make the comparison between all the three scenarios. So here we can see that global warming potential of nickel powder production for the three selected scenarios. So as expected, scenario number one has the highest impacts based on like the ore extraction and processing that raw material and also transporting that material from the mine to the manufacturing facility. Scenario number 2, again, as expected, has a better performance compared to scenario number 2 because it actually captures and uses the recycled material. But compared to scenario number 3, which has the lowest environmental impacts compared to the other two, scenario number 2 doesn't apply any carbon offsets to utilities and transportation. So here we can see the percentages and the relative environmental impact of these 3 scenarios. That under scenario number 2 compared to scenario number 1, we have 96.3% reduction in the environmental impacts, and in scenario number 3 we have 99.7% reduction, which mainly contributes to applying the carbon offsets to utilities and consumables and transportation activities. So here we have the main drivers of global warming potential for nickel powder production for 3 scenarios. So again, you can see that on the left, we have scenario number 1 using 100% virgin nickel, and that it actually has raw material extraction and all of those activities related to the raw material as the main driver. In scenario number 2, since we applied and we had multiple suppliers all around the US to provide that scrap material to the supplier, as well as one supplier in Canada, so you can see that transportation activity has the highest impact and is one of the main drivers, environmental drivers here. The second one is argon. So within this 3rd scenario, based on all of those carbon offsets to utilities and consumables, so you can see that the impact of argon or the consumables is pretty minimal. And again, transportation, although we have some local suppliers, is becoming one of the main drivers for the environmental impacts. So that being said, the findings of this study highlight the significant environmental benefits of utilizing recycled materials in nickel powder production, which can assist material procurement decisions. The powder phase, the production phase of virgin nickel contributes to over 96% of cradle to gate global warming potential environmental impacts. Also, 2 scenarios investigating circularity, means scenario number 2 and 3, demonstrated significant reductions in global warming potential, like 96.3% and 99.7% reduction respectively, compared to the first scenario, which mainly focused on using virgin nickel and going through all of those mine extraction and processing the raw material. And finally, this study supports the importance of circularity and sustainable manufacturing practices, which are crucial in addressing the challenges of resource depletion and climate change. That being said, here is like the end of this presentation. We'll happy to answer any questions.
All right, Kamyar and Carl, thank you for that very interesting presentation. So at this point, I think it's appropriate to reintroduce Dr. Sunil Badwe. Sunil, you represent Continuum on this. Can you talk a little bit about what's the role of Continuum in this specific assessment, and what are the differences in producing nickel powder from virgin material versus recycled sources?
Sure. Thank you, Scott, Kamyar, and Carl. So Continuum Powders basically is a gas atomizing company. So we also manufacture powder through gas atomizing. But Continuum Powder has a developed technology that can accept the scrap materials. So basically the recycled materials for upcycling into the metal powders. And generally speaking, when we say recycled powder, that's probably not a right term, because in what we produce at Continuum is a virgin powder, which is not being used for any other applications before. That's what we supply, but it is manufactured from recycled or it is upcycled from recycled materials, which are available abundantly in within the United States, right? So this technology is a little bit different than the conventional technologies where they cannot use directly the scrap. They can use indirectly, but then they have to put lots of processes and energy and ultimately larger carbon footprint to the final product. So in presentation from Kamyar, we saw that like first difference between the virgin raw materials and the scrap raw materials is the mining process, which is most environmentally unfriendly process, which can introduce lots of carbon emissions to the environment. So by using recycled materials, which are already pre-alloyed, that can reduce the environmental effect of carbon emissions tremendously. So that's the one step. And then we use plasma atomizing and cold hard process. So what that does is that these are used materials or recycled materials. So if there are some impurities in those materials which are heavier than the material being atomized, in this case it's nickel-based alloy, which because the cold hearth has a solid crust beneath the molten metal, which always remains solid. So these heavy impurities, they are sunk down and trapped in that crust, which are not part of the powder produced. And this is the similar technology that is being used for years for refining titanium. So this cold hard process is years long process and used for all titanium refining. And so that means that what we are melting scrap materials for atomizing, that not only we are just melting it, but also refining at the same time. That cuts all the steps in between, which are very energy consuming. And the other advantage of our system is we use plasma melting, which can evaporate the like light elements or organic impurities in the scrap, like oil or some other impurities. So we have advantages on both sides, and lighter impurities and heavier impurities. So that's the basic difference between conventional manufacturing and the manufacturing that Continuum has developed.
So I know from our perspective at additive manufacturing research, we do a lot of the tracking of the powders used in additive manufacturing processes by the different relevant metal families. Nickel powder tends to be one of the most important in this specific kind of technology. I would like to hear from maybe the OSU student, maybe also UCL as well. Why the focus on nickel specifically, or maybe why are we doing it now?
So let me see if I understood your question. So you're asking why the focus on nickel at this time? You're kind of fading in and out there. So
yeah, in the market, we've seen some other efforts for recycled and recycling processes for ultimately produce additive powders, but we haven't seen them, as much in nickel specifically. Is there a reason why nickel is kind of the initial focus of this study and one of the focuses of Continuum, and maybe can it be applied beyond that?
Oh, sure. Yeah. So, like Kamyar mentioned earlier in the presentation, kind of the importance of nickel, especially as an alloying element. And so in this particular study, we took the look of pure nickel, but you might actually be looking at a nickel-based super alloy. So there would be some more alloying that would come into play. And I think with what Sunil just talked about is an advantage here is that we can take in or Continuum can take in pre-alloyed materials that are of the alloy that you might like in a powder form, take them as scrap material to be recycled. So that offers a lot of advantages. More broadly, right now, there's a lot of emphasis on how do we improve the circularity of materials to take advantage of, you know, especially embodied energy within the materials that has gone through processing, rather than starting with a virgin material that requires a lot of energy input and you know, a lot of transportation that also adds a lot of cost along with it, as well as the environmental impacts that we were talking about. So you know, I think there's this case gives also a broader perspective of what we can be thinking about for different materials to improve the circularity and the ability to recover some of that energy that has already been invested in creating a new material.
Just to add more to what Carl just said, right? So why nickel first? So if you see the current additive manufacturing industry, so nickel-based alloys are like a major portion of additive industry right now. So those are the powders that are widely used. For example, Inconel 718 and 625, they are widely or percentage-wise mostly used for additive manufacturing. The second comes titanium. So this study, what it did for us or everyone, is that it provided a framework for calculation of greenhouse gases, right? So the calculation of carbon emission from a process that Continuum has developed. So this can easily be employed. That framework can be employed for any other alloys. So next one in our horizon is titanium alloy. So once the nickel is done, so then the second one is titanium. And then as we introduce more and more alloys, all those alloys will go through the same framework. Of course, they will have all different process parameters, so the numbers will change. But yes, basically, it can be used for any alloy that we can manufacture.
Great. So at this point, I'll remind the audience out there, you can submit some questions using the Q&A feature, and we actually have a few that have come in that I think are relevant to address right now. And this first one, Sunil, I think this one is going to be mostly directed towards you. Sure. An audience member asked, do you have issues with vaporization of some alloy elements during this process?
Yes, that's a good question, especially when we are talking about plasma melting. Generally in plasma melting, you see some vaporization of some metals, but the system that Continuum has developed is that at any given point, the material it's in molten state, not more than a few seconds. So basically we melt it very fast and we pour it very fast. So with that, the alloy doesn't get a time that is required for vaporization. So in our system, no, we don't see any vaporization of any alloys, especially nickel-based alloys, chromium, that is more vaporized than in titanium alloys, aluminum, that's vaporized. So we don't see any change in that.
Okay. And then we also had a question around costs. So this could be maybe directed to OSU as well as Sunil, depending on how you interpret the question. But the question as it reads is, what's the cost impact of this study? And I think it would be interesting to also hear about kind of relative costs of this type of process versus kind of like that scenario one, the classic process. You know, for the end user, as before we get to Michael, the material that is produced, are there notable cost impacts, you know, to using recycled materials, and do we want to address that at all?
So yeah, I will address it first, and then probably from your perspective, OSU, you can do that. The first one that I would say, okay, we have the elements, right? So for example, nickel-based alloys. So nickel is major element, and chromium and molybdenum and other elements are there. The prices for these elements are controlled by LME. That's the metal exchange, London Metal Exchange. So generally, the price fluctuations are based on the price in the London Metal Exchange. And whether it is coming from virgin metal or it is coming from scrap, the metal prices or element prices are calculated on that. So generally, even if we are using recycled material, that doesn't mean that it is much cheaper than using virgin metal. It just that the raw material is probably same, but there are steps. I mean, continuum process is one-step process. As I described before, we just take this recycled material and melt it and then produce powder. While the traditional processes can involve taking the scrap metals, adding virgin elements to it, and refining it, and then producing a feedstock, like in terms of ingots, and that is remelted to produce powders. So that process, that additional processes that cost more. But at the end, when we are in like consumer market or commercial market, so we still have to be competitive in the market for pricing.
Sure.
Yeah.
Carl,
So
Camille, do you have any? Yeah, go ahead.
yeah, I was just going to add that that's not something that we investigated in the scope of this project. And so I think Sunil gave a good answer there. You know, a lot of it is really market driven when it comes to cost and price of materials. But you have the opportunity here to shorten the supply chain, which can offer some cost advantages. So, you know, from a producer perspective, you know, there could be the possibility either to reduce your price or increase your profits on the materials that are produced. So, but that's not something that we had looked into in this project.
And on top of that, if you consider, right, so we have done this LCA study, so carbon footprint study. So this can be translated into the carbon credits. So that's what we are working on. This was the basis for looking the carbon credits. And when you get the carbon credits, I mean, lots of companies that have now initiatives for it from ESG point of view, reducing the total carbon footprint, and these carbon credits used towards that can be used towards that. So this is another advantage of this process.
Great. There's also a really good question here too that I actually had as well, and someone from the audience noticed it. And this would be for Camille or Carl. The yield in the LCA study, you mentioned 25% yield assumption. That is for a specific PSD, or what was the what was the yield as far as the PSD? Was there a specific one in mind for that?
Yeah, I think I can answer that. This is more on our side. So this 25% yield is on additive manufacturing, basically LPBF cut, normally 15 to 45 microns.
Got it. Okay, 15 to 45. So kind of the standard, PBF.
Yeah, LPBF cut.
Okay. So now we're a little more than halfway through. I want to kind of transition now. The study we saw gives us some good data and some highlights some of the powerful impacts. But that's kind of one side of the equation, and then the other side that we really want to hear about is kind of the real world impacts. The shop floor and how we can apply that. So for that we have Mike Forelli, who is president of Rev-Tec. He's seen firsthand how reclaimed powder like this performs in kind of like that real world environment. So we'd like to bring Mike into the discussion now. Mike, tell us a little bit about Rev-Tec first of all, and what your company manufactures, and maybe kind of how you're how you interacted with this team and your role in all this.
Sure, Scott. Well, Revolutionary Technologies, or Rev-Tec, we started off as an engineering design firm who transitioned into, we were a job shop with Subtractive, and we had designed some people had come to us to design some parts for us, and they liked it, and they had asked us to manufacture it for them. And at that time, we said that we couldn't because we didn't have the 3D printers, and they sort of made us an offer we couldn't refuse, so we got into additive manufacturing, which sort of blossomed And that was only 2 years ago. So we went from having one machine, an EOS 300, to I currently have 3. And next week I have 2 more being delivered. So it's right now it is the industry. This is the technology that manufacturing is trending towards. It gives engineers the capabilities of what once could only be done on a CAD or a simulation, and the in-house machinist said I can't do it. To okay, we put it on a machine and here it is. Something that can't be made through subtractive is now in front of you. It's a game changer for the industry.
Sure.
We do this type of work for pretty much everyone from the DoD, oil and gas industry, and then recently we're getting into automotive also, because it's getting into that sector now where the internal combustion, flow through designs, pressure, we could create flow restrictors that you can't machine. So that's where we're heading with this.
Yeah, I think you have a a really unique perspective, considering that a lot of the messaging in the industry, especially the additive side of things, is it's challenging, and there's not the growth is out there, and the interest is definitely out there, and a lot of times the disconnect is just kind of figuring out how to capitalize on that, and from the technical perspective, how to make it all work. One of the things I wanted to ask you, Mike, as well, is about powder sourcing. So, this is something relatively new to you guys. The powder sourcing piece, how does that factor into the growth that you're trying to leverage here with 3D printing, and if there's a role that powder sustainability or reclaimed material plays in that decision making?
Yeah. So when we started off, every manufacturer out there has sole source, you could say, on the printer side. They have one powder that they recommend, and you buy it through them. And because that's the game you play. And last year we started looking into it because we were having delays on receiving our raw materials. And I started looking and actually found Continuum, and we discussed my needs and how fast I do it, because I have bi-weekly deliveries, just to make sure I keep underneath any flammability thresholds inside the building, which now have moved to having a Connex outside, so I can store more. But what Continuum has done is delivered to me when I need it, when they say they're going to deliver. So I know anywhere between Thursday and Friday, I'm going to have my delivery. We've set it up so that it's freight, trying to reduce as much. Why add carbon to the system when they've already taken it out? So we've already scheduled it out. We know exactly how long it's going to take to ship from Texas to our New Hampshire facility, or from California. When other companies, we would call up and say, hey, we need this, they could be out, or they wouldn't have the material for us for 2 weeks. Well, it's the same scenario as if you're in subtractive. Having no powder means that the machine's down. Similar to if you're in subtractive, it's spindle down. You're not turning, you're not making any money. We're running our machines 24/7. That's the beauty about additive, and Continuum's been there and supplying us. We do our 718 as well as our TI-64 with them.
Great. Are there any other powder supplier criteria maybe that you might have already had in place, or that you're developing, that you think is important for companies out there and for users out there also to have, maybe that Continuum also met as well?
Continuum offered us what no one else could. They allowed us to pick the range, our PSD size. When everyone else out there says, all right, here's the ASTM spec, this is what we're going to give you, and you can send it out, which everyone else does, is you send it out to a third party to verify, and you watch your the chart, oh, it's supposed to be 15 to 45. Well, there's 5% and under 5, and you're above the 45, and you're looking at it with, working with Sunil, they held it where we wanted. So when we sent it out to third-party testing, everything came back in spec how we wanted it. We are bringing some of that testing in-house, just so we have the availability also. But we also have a material analyzer system on hand. So we'll actually test all the samples to make sure it is what it is. Because in the beginning, there was the fear of, all right, is there something else getting into our 718, just in case? Because you could start a build, and for us, a lot of our builds are 42 to 54 hours, and you don't need anything in that to potentially ruin that build, because at that point, it's all lost. And we haven't had any of those issues with the recycled powder from Continuum.
I want to talk a little bit more for sure about the properties of the powders and your perspective on those, Michael. But before I do that, you mentioned something interesting about being able to continue being able to basically meet a custom PSD, right? Not necessarily the kind of typical, and that is something that at Additive Manufacturing Research we've heard, for several years about. That's kind of one of the challenges that are out there. It makes more sense to get tighter and tighter PSDs in some scenarios, some applications, but sometimes that's a challenge to deliver. Sunil, is there anything specific about the Continuum, the M2P process that enables that, or is that something that you guys are going to be able to continue to deliver in the future? Talk about that for just a minute.
Yes, so our M2P process, so basically we call Greyhound our atomizer. So first thing is that it's very small footprint, so we can deliver faster, as Michael said, right? So if he has some other requirement, we can tweak our atomizing parameters for particle size change. But ultimately, we have to sieve it to control the particle size. So that, we do that, everyone else do. But what we do differently is that we tweak some atomizing parameters that enables us to maintain or improve the yields within that sieving portion. So for example, this is 15 to 45. So we can tweak parameters and make this yield or vary that yield, whether it's go up and down. So based on requirements like Michael, so we can tweak our parameters and then deliver that. And this is the other thing that what Michael mentioned, that he had a fear initially that because there is powder made from recycled material, that anything other than alloy that goes in there and that ruins his print. So that's normal fear from everyone when we say recycled powder. But as I mentioned before, that we use recycled raw materials to make a virgin powder. So while we are doing that, so because we have a cold hard process, so while we are melting it and atomizing it, at the same time we are refining the process. So nothing else other than the pre-alloyed metal that goes into final powder.
Okay. We've had some good questions also related to this kind of particular vein of the discussion. Sunil, when referring to recycled nickel, this is coming from the audience, are you referring to pure nickel, or are you referring to like a nickel alloy-based scrap like 718?
Yeah, so we are talking about nickel alloys because those are widely used in the industry. But for the study, we consider nickel pure nickel because that's easier to get the data, and that there is abundant data on pure nickel powder historically. But since this nickel-based superalloys are about 60% nickel in there, so this generally applies for all nickel-based alloys.
Okay, and there was also a question about vacuum induction furnace versus plasma melting. Which one of those is more suitable for the scrap melting specifically, considering the different impurities present in the scrap?
So more importantly, it's not just about the impurities, but it's about the form factor. Because when we say scrap or recycled material, that comes in various forms. So it can come in machine chopped chips, turnings, or it can come from like rejected parts, end of life parts, or failed builds, support structure. There are various kinds, even the used powder, right? So from the traditional kind of induction type furnace. That induction type furnaces based on principle of eddy current, so induction, right? So for that, it is preferred to be a solid scrap, that when you fill that crucible with solid material, that's a more efficient way to do that. So if, for example, if we have a bunch of powder, it can be used at some percentage in the induction furnace or vacuum induction furnace, but you cannot use that 100%. You have to supplement that with the solid material. But in the cold hard plasma melting, it is form factor agnostic. That means you can put anything in there, any form recycled material, as long as the chemistry is within the specifications. See, because this process just cannot add elements or remove elements from that. So what chemistry goes in, that chemistry comes out. As long as its chemistry is fine, any form factor can be used in cold hard plasma processing. So yeah, so I think there is one more question here. So the question is, what are the challenges in melting and refining nickel scrap and before atomization? In our system, as I explained before, it is form factor agnostic. So we can essentially use any type of scrap form factor, but depending on the form factor, we'll need to pre-process that. So basically, we have a feeder. So anything, if it is a big casting, then we have to cut it up to fit in that feeder. If it is powder or chips, the machining chips, then we have to bundle it to go to the like a solid, semi-solid block or puck that can be feed easily for handling purposes. But other than that, there are not challenges.
Looks like there's a new question there, Sunil. What are your limits for selecting scrap material in regards to chemistry, for example, gases?
Yeah, that's interesting questions. As far as the chemistry is concerned, if we are talking about the base chemistry, as I said, it is chemistry in and chemistry out. So we cannot add or remove any elements. But in case of gases, especially oxygen, so we have ability to reduce oxygen during our process, during our one-step process. That's especially useful for titanium recycling. And when we talk about titanium recycling, that is a major hurdle in recycling titanium because of the oxygen content. As we process titanium, it becomes scrap. The oxygen content of that titanium is increased. So we have ability to reduce oxygen in the scrap and form and make a powder with it, which is within the specifications of regular titanium 64 grade 5 or grade 23.
Yeah, there's another question here that talks about the LCA, and maybe this is one that Kamyar can chime in on, and maybe Sunil, you have some thoughts also. So from the LCA analysis, there's significant differences in carbon footprint reduction for the various sources, or is there a significant difference for different sources of materials? For example, using swarf versus used parts. I know in our study, this isn't something that we considered, so maybe Sunil, you have some thoughts there.
Yeah. So yeah, I mean, obviously we can process all of that, right? So the major portion of our difference between processing scrap and solid materials that come from the the energy consumptions. So the energy consumption per kilogram of melted material. So if we have a loose swarf and low density material, that will consume a little bit more energy to melt that down to desired temperature as against the solid scrap metal. But in our case, as Kamera described, scenario number 3, where we are considering the carbon offsets, right? So the carbon offsets means what we are considering there is green energy and green argon that is used in our Houston site. And at the same time, we are considering carbon offsets for transportation, as many of the scrap suppliers or our raw material suppliers are located within about 50 miles from our factory in Houston. So the transportation costs, which are like scope 3 emissions, indirect emission calculations, so they are reduced. And also we reduce the energy carbon footprint of energy, because we use green energy, 100% green energy, and we use 100% green argon. So automation and process losses are probably more. Our energy consumption in the process is a little more while using swarf and solid metals. But as far as the carbon footprint or LCA study is concerned, there is no difference.
Hey guys, I'm back. Sorry about the technical difficulties there. I lost the discussion very briefly. I didn't know if we had a chance, but one thing that I really wanted to ask Michael as well is if he's had a chance to compare kind of like traditionally produced nickel powders versus the powders produced from scrap from Continuum. Is there any thoughts or comparisons there, Michael, if you've had a chance to do that?
Yeah, we've done that with multiple companies. That's actually one of our deciding factors. Before we went to Continuum, we compared their product to about 3 others that were readily available. And there was no inconsistency that made them stand out if we were to do a blind test. So that was basically the final decision we made to go with them.
Awesome. Are there metrics, maybe like flowability, PSD analysis, other stuff that have been most valuable in tracking the quality of this reclaimed powder over time? Anything that stands out maybe from those?
We do a flow check. That's more of an internal thing. That's how we know when to stop utilizing it. Because we're also doing a sieve after every single time, because we reclaim it ourselves, so we can recycle as much as we can, and that's how we know. But when it's finished, we also look at any particles. You could call it, abnormalities. We look at it through a microscope and see if it's any shape changes or whatnot, and that's how we know when to, it's time to retire the powder. And it's with Continuum, it's a nice way, because there's a lot of scrap vendors out there that don't know how to handle powder. Even though it is metal, they don't want it. Had a couple in our region that actually didn't even want to take our failed builds, because to them it was made through additive, so it must be different, even though you can scan it. It's a solid piece of metal. There's no difference. But with Continuum, we keep it all separate, and they take it back, so it's a closed loop system with them.
Great. We're coming down to the end here, so if you're in the audience and you have any remaining questions, we might be able to get to 1 or 2 more before the time. We do have one that I think is interesting, related to the chemistry composition and controlling and repeatability of that. Does that become more of an issue? I assume this is more for Sunil. Does that become more of an issue with this process, kind of the composition and controlling that and keeping it repeatable?
Yeah, that's an interesting question. And as I said, our system is chemistry in, chemistry out. So that becomes important for us to control the chemistry of raw material, what we use. So it is extensively analyzed before we take any of the material, like what Mike has said, right? So even if he has segregated the material that on his side, so when we take that material in, we analyze that thoroughly before we put it in our reactor or our atomizer. So So the extensive chemical analysis is done on incoming raw materials. That's what we use. Otherwise, we don't want to use any of that material that what we are putting in our system that will destroy the whole batch of the of powder. And at the same time, when we produce our powder and lot it, so we have another chemistry check or basically whole powder analysis when we produce powder and before we ship to anybody.
Great. Let's see. Maybe to close the panel out a little bit. Michael, I think your perspective is super valuable here because we can talk about processes, but it doesn't necessarily mean that much if it's not going to satisfy the needs of the people who are actually out there, using the powders and ultimately satisfying your customers' needs. So from what we've heard today, it sounds like this is has worked super well for you in part because it's available and it's on time and everything is delivered as as expected, and it works perfectly well. Cost wise, it sounds like it is if not comparable, perhaps there's some possible future cost advantages to this, which I think are important as well for the market. Any closing thoughts, Michael, as far as scrap sources of material or powder produced from scrap sources of material? Is this a viable thing going forward long term? And is this something that you guys are going to continue to seek out in the future? Or any advice for other users out there, maybe along these lines that they should look out for?
Sure. It's for us, it's definitely the way we're going forward with it, just because it's a closer network, especially seeing how it's a closed loop where Continuum takes back our stuff. I can't go to any other place or the local metal yard and say, all right, here's my cut ends. Can you please trade me in another 12-foot bar stock? It doesn't work that way, but here it does. The other thing to go, we utilize it. So that was the hard part. What Continuum is, getting someone to trust that process, that it's recycled. So we did our research to the point where we told, because we're ISO and AS certified flow down, we had to tell everyone, all right, this is our powder. They're good with it. When we made that switch, we had some pushback. Well, is it the same? Is there going to be any issues? We actually did side-by-side, prints in two different machines with our current source and this source, and gave it out to our customers for them to test so that they could be comfortable with it also. And they soon saw no difference in it as well. And it's also at this point, because they are, making it out of plasma, it's now considered U.S. sourced.
Yes.
So it's no longer, it falls under DFARS, it falls under anything else to do domestic work for the DOD or aerospace. They may have that on a flow down. So for us, it's been a really good choice for us since the beginning of the year.
Awesome. Well, that was really, really valuable perspective, Michael. For the audience out there, we appreciate your attention this afternoon. We've got some contact info on the screen here in case you want to get in contact, maybe address some more of the questions. I think there might have been maybe one or two that we didn't quite get to. So please feel free to reach out to the team at Continuum, and they'd be happy to help. So with that, this is going to conclude the presentation for this afternoon. Thank you all for your attention, and definitely thank you to the various presenters and speakers. I know I learned a lot, so I really appreciate it, and everybody have a great afternoon. Thanks.
Thank you.